All right, so today we're going to talk about rotational energy on an incline, setting up for our rolling on a ramp lab. So with this, everything that we're going to do here today is almost an alternative to what we did last unit with torque. So the difference is you still need to know how to solve for the acceleration on this ramp using torque, because if they ask you to find the torque or the acceleration, then using the method from last unit where you define your forces is going to be generally easier, although you can always work your way backwards. So essentially what we're going to assume is that we are still going to have the rolling without slipping. And then we have two cases. We have rolling up the ramp and we have rolling down the ramp. So in the first, let's just look at rolling up the ramp. So if I have rolling up the ramp, then what I'm going to assume is that this object is going to start rolling already in motion. So it's going to have some sort of velocity for its center mass, and it is going to have some sort of angular speed. So it's already going to start with some rotational kinetic energy. And then what's going to happen is essentially its center of mass is going to increase in height. So if you define like y equals 0 and then like say y equals h, and you're on some angled ramp theta, then the center of mass of whatever this rolling object is going to change heights. So you're going to start off with, if we look at like an energy diagram, when we see that they're rolling without slipping, there's no loss to friction, so our work is actually going to be 0. And at the start, we are actually going to have potential energy, rotational kinetic energy, and translational kinetic energy. At the end, we could have potential, rotational, and translational kinetic energy. It should be like a 1 right there. So we're going to assume here at the bottom that when y equals 0 that our potential energy is equal to 0. So I'm going to start off with no gravitational potential energy. Now I am looking at the Earth ball system, so that way gravity is contributing to potential energy, not work. But I'm just going to assume that my center of mass is as low as it can go. And then it's going to have some amount of potential of kinetic energy, K trans and K rot. These don't have to be equal. The ratio of the translational and rotational kinetic energy is going to depend on the coefficient. So, because we're always going to be able to relate the velocity of the center of mass to our angular velocity. So for example, if this was a hoop, then the total kinetic energy at the start, I'd have translational kinetic energy equal to 1/2 mv squared, where that v is the velocity of the center of mass, and then I would have rotational kinetic energy at the start equal to 1/2. And then if this is a hoop, it's gonna be I omega squared, and that I is gonna be mr squared. And then we can always represent the velocity of our center of mass as equaling r omega, so I can find that omega is gonna equal VCM over r. So I can convert and compare these two by making my omega VCM squared over r squared. And you can see that what happens is that r squared cancels out. So I find that my rotational kinetic energy is equal to 1/2 m VCM squared. So if I have a hoop, exactly half of my kinetic energy is translational and the other half of my kinetic energy is rotational. So in that case, if this is a hoop, those two are going to start off equal. What about if it's not a hoop? What if this was, say, a cylinder? Well, if it was a cylinder, so say it's a solid cylinder, a disc, then my translational kinetic energy is still going to be 1/2 mv center mass squared. But my rotational kinetic energy is going to be 1/2 I omega squared, which is going to be 1/2 times 1/2 mr squared, and then omega squared is going to be that VCM squared over r squared. So one thing that I often forget to do is when I do the solid cylinders, I'll do 1/2, and then I'll forget the 1/2 for the rotational inertia. So be very careful when you're subbing in that you actually sub in the full formula. So in this case, once again, the r squareds are going to cancel. So we've already figured out that when we did acceleration, that the radius of the rolling object doesn't actually matter. And actually the mass cancels out too. once you sub in your formula for your rotational inertia. So then if I look here, I'm going to end up with 1/4 VCM squared. So if this was a solid cylinder, if I have some amount of translational kinetic energy, I have actually a total of, when I look at like K total, that's going to be K trans plus K rot, which would be 1/2 m VCM squared plus 1/4 m VCM squared. So my rotational kinetic energy in total, if I make this 2/4, is going to be 3/4 m VCM squared. So in that case, if I look at my translational kinetic energy, 2/3 of my translational kinetic energy, my total kinetic energy is translational, where only 1/3 is going to be rotational. So in this case, I have something along this lines, where a cylinder, where these are not equal. But when you draw your work energy diagram, it is not necessary to specify exactly how much there are. It's helpful. They'll ask you a lot of questions like, what fraction of my total kinetic energy is rotational or is translational? So you'll have to kind of do this kind of analysis. But if you're just drawing a diagram, you don't have to have exact values. But the idea is as this thing rolls and it gets to the top, as we know that there's going to be a net torque that is causing an angular acceleration in the opposite direction. So that due to that friction force going up the ramp. So what's going to happen is it's going to start to slow down rotationally. But then our linear acceleration of our center of mass is related. Remember, the acceleration of the center of mass is going to be r alpha. So you have that same relationship, but that's going to be downward. So our linear velocity is also going to slow down. So that basically when it reaches the top, there is no linear or rotational speed. So that means whatever energy we had at the start is now all in potential energy, because both our translational and our rotational kinetic energy are zero. Now, essentially what's going to happen is, depending on what I have, if I have, say, two objects that have the exact same speed, so if the K trans is the same for the hoop and for the, say, the solid cylinder, the hoop is going to have more rotational energy because of its larger moment of inertia, but they'll have the same translational kinetic energy. So if the hoop has, the hoop would have, at this point right here, the hoop would have a total energy. We said they were both equal to 1/2 mv squared. So the hoop would have K total equal to just m VCM squared. But my cylinder, even though its velocity of its center of mass is the same, and it would have maybe the same mass and same radius, its K total is only equal to 3/4 m VCM squared. So the hoop is going to have a larger total amount of energy to start with, which means it's going to be able to generate more potential energy. And a hoop is going to travel further up this ramp before it comes to stop than this cylinder. If I had a solid sphere, the solid sphere has an even smaller rotational inertia than the cylinder, which means the solid sphere is going to stop even earlier than the cylinder. So, and that's if they're all starting with the same speed. So going up the ramp, basically, because your total energy that you have at the start is determined by your linear speed, the more rotational speed you have on top of that linear speed based on your rotational inertia, the more total energy you're going to have. So objects with higher rotational inertia moving at the same speed will have a higher total energy available to them. So that's why the hoop would kind of be able to continue further up that ramp before stopping. Now let's look at what happens when you go down the ramp. All right, so if I'm looking at motion down the ramp, then what I'm going to assume in this case is that I'm going to start at some height. So I'm going to have y0 equal to some height here, and then this thing's going to roll down the ramp, and at some point in time, which we call y equals 0, we are going to be at the bottom. So we're going to start off with the linear speed equal to 0 and our angular speed equal to 0. So it's not rotating at all. So we know that if I was to release this from rest, that there's going to be a linear acceleration down the ramp, and that as long as we're rolling without slipping, because there's a friction force up there, that's going to cause an angular acceleration in the same direction. So that means that this thing is going to speed up both linearly and rotationally. So that at the bottom, your center mass is going to have some sort of speed, and then you're going to end up with the angular velocity in the same direction as your angular acceleration was. So if I have different objects, they're all going to start off with these, if they have the same mass, they're all going to start off with, say, the exact same amount of gravitational potential energy. And they're not going to start off with any rotational energy. And then we can assume that if we define our potential energy equals to 0 whenever y is 0, then we're going to have no potential energy, which means we would have had to convert all of our potential energy into both rotational and translational kinetic energy. So same idea is true with going up the ramp as down the ramp, is that my total kinetic energy is going to be the sum of k trans and k rot. Now, if this ramp was frictionless, then there would be no rotational kinetic energy. And that means that when I reach the bottom, oh, no, wrong spot. There'd be no rotational kinetic energy at all. So that means whatever energy I have is going to equal to, it's going to be translational kinetic energy, is going to be equal to my initial potential energy. So if I'm rolling, basically what I'm doing is I am stealing some of the kinetic energy I would have had from translational energy and converting it into rotational kinetic energy. So what that means is I'm going to have a smaller amount of translational kinetic energy at the bottom, which means the linear speed that it's moving is going to be smaller than if it was sliding down a frictionless ramp. So an object sliding down a frictionless ramp is always going to have a larger speed than any object rolling down the same ramp. And that's because, remember that based on the acceleration, that if it's a frictionless ramp, your acceleration is g sine theta. And if you're rolling, your acceleration is something like, I think it's like 1 over 1 plus x times g sine theta, where x is that fraction for the coefficient in front of your rotational inertia. So this is always going to be less than 1, which means that your acceleration when you're rolling is going to be smaller. So you're going to get a smaller linear speed at the bottom. So from an energy standpoint, the same thing's true. So basically, my total energy is getting now split. So the larger the rotational inertia, I have, the more energy you have in your rotational kinetic energy. So if I have a larger rotational inertia, I'm going to have more rotational kinetic energy, which means I'm going to have less translational kinetic energy, which means I am going to have a slower linear speed at the bottom of the ramp. So if you remember back to the rolling on a ramp demonstration that I did, where you took the hoop and the cylinder and rolled them down the ramp, the hoop was really slow to start, and the cylinder beat the hoop down the ramp every time. And that's because for the hoop, more of its energy was rotational because of the larger rotational inertia, so it had less translational rotational energy, less translational kinetic energy, and therefore a slower velocity of the center of mass. So conceptually, that's what's going on. So rotational inertia is resistance to change in motion. So going up the ramp, the object that has more rotational inertia, assuming they were going the same speed initially, is going to be able to travel up the ramp further before it stops because it has a larger amount of energy, and it also has more resistance to slowing, to changing its motion. Whereas when you're looking at going down the ramp, the object that has the larger rotational inertia starts off with the same amount of gravitational potential energy, but it has to transfer more of its energy into rotation because of the larger rotational inertia. So therefore, it's going to end up with a smaller speed at the bottom. So those are like really important concepts. Now, if you were to actually solve a problem with potential energy, so say you wanted to find that speed at the bottom, you would essentially set up your equation here where I'd have my potential energy at the start is equal to k rot at the end plus k trans at the end. My potential energy at the start is going to be mgh. Be aware that sometimes they don't give you height, sometimes they give you length and an angle of a ramp. So you might actually have to calculate the height in that case. But in either way, you can find the height. Your rotational kinetic energy is going to be 1/2 I omega squared. Your translational kinetic energy is going to be 1/2 mv squared, and that's v of the center of mass. I always like to remind myself of that. So if I wanted to say find the linear speed at the bottom, I would convert my angular speed into a linear speed by using VCM is equal to r times omega. So omega is going to be VCM over r. So I can sub in, so mgh is equal to 1/2. And then for my rotational inertia this time, I'm just going to use a general x, mr squared, where x is that coefficient in front that is dependent, like if it's a hoop, it's a 1, if it's a solid cylinder, it's a 1/2, if it's a solid sphere, it's a 2/5. And then my omega squared is going to be VCM squared over r squared, because I'm going to have to square both terms, plus 1/2 m VCM squared. So all I've done here is sub in for rotational inertia and converted my omega into a VCM. Now, if I wanted to find my angular speed at the bottom and I didn't care about my linear speed, instead of subbing in for omega with this, I would replace VCM with r omega, and then I could solve for omega first rather than VCM. But in this case, I wanted to find my linear speed. And when I do that, I get r squared canceling, so the radius doesn't matter. You can also see that mass cancels out, which is good because with conservation of energy, when we did this on ramps before, mass never mattered. It was independent of mass. So then if you look at this, you're going to get g times h is going to be 1/2 x VCM squared plus 1/2 of VCM squared. So I can come over here and I can group like terms, and I can get GH is equal to 1/2 VCM squared times x plus 1. And I can multiply by 2. I get 2GH is equal to VCM squared. And then I can divide by the x plus 1, or I'll do 1 plus x because I like that better. And then I can take the square root of both sides. So I find that the velocity of my center mass is going to be the square root of 2gh over 1 plus x. So what's going to happen is that the larger the coefficient of my rotational inertia, the smaller the VCM. So your largest coefficient would be for a hoop, which would be a 1. One of your smaller ones would be, say like the solid sphere. That would be the 2/5. So that would cause you to have a different relationship. So the larger your x value, basically the larger your denominator, so therefore the smaller the velocity of the center of mass. Now, if this was not rolling, because it was a frictionless ramp, then this term goes to 0, and you just get that the velocity of the center of mass is the square root of 2gh. This is an amazing value. We've seen this so many times. We saw this in our video yesterday, that if you were to drop an object, then the speed it would have at the bottom is going to equal the square root of 2gh. So if I drop this object, so if this was a ball and I released it from rest, and it just fell, the speed at the bottom would be the square root of 2gh. If this is a frictionless ramp, if I release this from this height and it goes down to that exact same height, but it goes on a ramp, it's going to have the exact same speed, square root of 2gh at the bottom. What's really cool is if I do a pendulum, and I have a height here, that the speed at the bottom here is also the square root of 2gh. And that's because all three of these situations, you're starting off with the same amount of potential energy, and you'll have the same amount of kinetic energy at the bottom. The only difference is this case of rolling, or the example we looked at yesterday where this object was connected to a pulley, is that when you add in the fact that there's rolling going on, so in this case rotation for the pulley, or rolling here, that the rotational inertia of the object is going to cause the linear motion to decrease and be smaller than the square root of 2gh. So if ever you're working a problem and you're running out of time to do a calculation, just realize that your answer for any sort of problem involving rolling is going to have a speed that's lower than the square root of 2gh, because square root of 2gh would be if it was just falling sliding frictionlessly or swinging on an angle. So there you go. There's rotational energy on an incline.